Okay, in this podcast we're going to talk about electron affinity, and this is still part of Unit 1, and if you want to read in the text, it's Section 7.5. Okay, so electron affinity is defined as the energy change accompanying the addition of an electron to a gaseous atom. So here I have a chlorine atom, add an electron, and I end up with the chlorine anion. If we look at the look up the definition of affinity, it says a spontaneous or natural liking or sympathy. Okay, because that's what we're looking at. How much does an atom like or want in an electron? Okay. Okay. And of course, atoms don't have feelings, but that's really what it is. It's about how much more stable they become when they add an electron. So, one of the most important things for you to get out of this course is that whenever you break something apart, it takes energy to make that happen. And anytime something combines, it releases energy. Almost always, okay? The reason it combines is to make it more stable. And more stable means lower in energy, and that energy gets released, okay? So electron affinity, in general, releases energy, is exothermic. But, of course, there are exceptions. Okay, so combining things releases energy. Electron affinity, therefore, tends to be exothermic. So if I take fluorine, I actually meant to change that to chlorine. If I take chlorine, add an electron, I release 349 kilojoules per mole. Okay? If I am talking about adding an electron to an atom that will not become more stable, that causes instability, it can be forced, but doing so will require you to put energy in. Okay? So if you think about taking a noble gas and forcing it to take on an electron, very difficult to do. It doesn't want to. It's going to become far less stable. So that is when it becomes endothermic. It requires you to put some energy in to make that happen. It's not a natural process. It's not spontaneous. Okay? Okay, suppose you were asked for the value of the first ionization energy of chlorine and of the chlorine ion, and what is the relationship between that quantity and the electron affinity? So think about that for a sec. Okay, so for the chlorine minus, and I want the first ionization energy, what that means is it's going to be losing an electron, so that's what I'm going to have. Electron affinity means I start with chlorine and I add an electron and I get the chlorine ion. If you look at these two equations, they are the opposite of each other. And whenever that happens, whatever the kilojoules is going this way is the negative of the kilojoules going that way. So they are equal in magnitude and opposite in direction. Okay, and actually, this is the one that would be negative because it's going to be exothermic. It's going to be more favorable, and the removing an electron is going to be endothermic. Okay. Okay, so if we look at this table, what you see is, in general, your electron affinity goes up as you go to the right, right? And it goes down a little bit as you go down. So think about this. So, a fluorine atom is much more likely to take on an electron and become stable than something like a lithium atom, right? Lithium does not become more stable with an electron. So it's going to take more energy as you get closer to that noble gas configuration. And of course, when you get to the noble gas, they are already stable. Adding electrons is going to make them totally unstable. Okay, and if you think about going down, let's just think about the halogens, because usually when we're talking about electron affinity, we're talking about halogens. The atom that becomes the most stable by adding an atom is fluorine. And that's, if you think about it, you know, it's in a shell it's got 8 valence electrons. All the halogens have 7 valence electrons. This is a mess. And adding one more makes it more stable because you're talking about attraction with the nucleus there, right? So if I'm adding an electron way out here, more energy levels away with iodine to complete that octet, the attraction to the nucleus is further away and therefore a little bit weaker. So fluorine is the high here. So let's talk about the exceptions. So of course noble gases, it's going to be endothermic. It's going to take energy to make them unstable. The other thing that happens, if I'm beryllium, if I'm to have the atom beryllium, it has a 2s2 electron, and if I'm going to add another, I'm going to add it to 2p. So the 2s2 is much more stable than a partially filled p orbital, which is going to be a higher energy. The same thing will happen here around, if we think about nitrogen. So nitrogen has a 2p3, right? So it's got 1, 2, 3. If I add one more electron, I'm going to move away from this fairly stable configuration to one where I have a situation where one orbital is full and the others are half full, which is less stable. Okay, we've seen that exception before. So those are the exceptions. Okay, so based on this periodic trend, which of the following elements is expected to have the highest or most negative electron affinity? So think about that for a sec. Okay, if we take a look at this, I've marked in red the 4 atoms that are, or elements that are in question. So we have sodium and potassium, and of course we know that the higher periods are going to have more electron affinity. There's going to be more attraction to the nucleus. And we also know that as we go across, that the electron affinity is going to go up. So the highest here is going to be sulfur. All right, we're going to stop right there.